Hello dear student, here's one doubt asked by some of you. So you can pause read this question, it's a good one, and let me explain what the question says, then again we will solve it. So there are two figures given in this picture, so this is not valid for this particular question. Only we need to focus on the figure 1.67, so this is figure 1.67. And it says we have a solid uniform cylinder, so that's a cross-sectional view of solid cylinder, and its radius is known to us, and this is rolling, so it's a rolling motion over horizontal plane surface, which is having an inclination, this edge, and this angle alpha is given to us as a 30 degree. And now we need to find the maximum value of the velocity v naught. So it's a rolling with velocity v naught. We need to find the maximum value of this v naught. That is permissible so that it does not jump. So this crosses this edge without jumping, and it keeps on rolling for future as well. So why it is asking for minimum value? Let's think about it's asking for maximum value. Why it is asking for the maximum value? So maximum means we need to find largest value which is possible so that it does not jump. Meaning is, if we increase the velocity beyond that maximum value, then you'll find if it is rolling faster, then it may jump like this. So that means at this edge it may lose the contact. So what we need to ensure that when it is crossing this edge, the contact, that means normal reaction, is not missed, particularly just after crossing this edge point. That means as this solid cylinder reaches to this inclined surface, it should not lose its normal reaction. So that's the condition is going to be for getting the maximum velocity permissible, and rolling has to be ensured altogether. So again I have solved this. This was the explanation of the question itself. Let me show that figure, the slide, and explain how the solution goes. So here the solution is mentioned. So what we are going to consider, we are going to consider three close figures, consecutive figures. One is indicating just before the edge is arrived. Two is indicating when the cylinder reaches to just at the edge, and the third is indicating just crossing the edge, that means landing on the inclined plane. So these three figures we need to watch, though I have shown in by certain distance, but we are considering it just close to each other. Now if you observe how center of mass is going to go, so center of mass is going to move in a straight line initially, then it is going to take a curve, and then again it's going to move on a straight line. So in between, when this edge is being crossed, you will find center of mass is going to move in an arc, circular arc of radius. That radius is going to be r. Now the motion of the or the trajectory of the center of mass for this transition has been shown over here. This is for the 1 position, this is for the 2 position, this is for the 3 position. This is how center of mass is moving. Now this angle is alpha, that is known to us, so we can say this angle is going to be 90 minus alpha, because when we are joining this, that means we are on the perpendicular to this inclined plane. So that radius is going to be perpendicular. This radius was perpendicular to the first plane, and the 2 figure is indicating somewhere in between. So from 1 it has gone to 3, then it will keep on moving with this 3. So from 1 to 3 there has been some drop in gravitational potential energy that would cause to increase the velocity v. So point is, we can go for mechanical energy conservation between the position 1 and position 3 of this solid cylinder, 1 and 3, just before the edge and just after the edge. Now mechanical energy conservation uses kinetic energy and potential energy. Kinetic energy uses both translational as well as rotational, since in case of rolling the total kinetic energy of solid uniform cylinder is given by 3 by 4 mv square. So we will write the kinetic energy of the solid cylinder which is rolling as 3 by 4 mv square. We should not write as a half mv square because that's only for translation. Or what you can do is write half mv square for translation plus half I omega square, then apply the condition for rolling, you will get same energy back. You must be remembering this as expression, final expression for total kinetic energy. When it comes to the 3 position Then the kinetic energy of total, in this case rolling, is going to be 3 by 4 mv square. V is the velocity of rolling. At the same time, you'll find this center of mass has come downside, so that means there is a drop in the gravitational potential energy, so minus mgh. How much the drop is? So this total was r, and this leftover is r cos alpha. From this triangle you can see this triangle, and from here we can find out this is going to be r cos alpha, so exactly the same as here. Leftover is h. This h is going to be total r minus r cos alpha, that can be written as r in then bracket 1 minus cos alpha, you know that. Now this is very important relation we are getting. Then we can simplify this in this format, and we can call this as equation number A. So we got an equation number A, and we have two unknowns. One is V, and another unknown is V naught. We need to find this the maximum value of this V naught. Now consider the free body diagram of cylinder when it is at the position 3, where the normal reaction otherwise would have lost if it is jumping. So we need to say this normal reaction is there. So if we draw the free body diagram, then you'll find what are the forces. Let me explain the forces. This is FBD cylinder. Mg will have a two component, cos alpha, sin alpha, you know that. Friction will be acting for rolling, you know, inclined friction has to be there and upwards. There is going to be normal reaction coming from the this inclined plane, as well as this is just moving on the arc, circular arc, so there has to be centrifugal force, and this centrifugal force is going to be mv square by r. Now this centrifugal force, if becomes more, that may allow this normal reaction to 0, that means it may lift off. So we say the forces must be balanced in this direction, so we are balancing the forces. Forces is going to be n plus mv square by r must be balancing mg cos alpha. This is equation number B. Now we say we don't want this jumping to happen, that means normal reaction must be non-zero, or we can say it should be non-negative. Basically this should be greater than or equal to 0. So equality is just for the limiting condition, that means for maximum permissible value, otherwise should be greater than. So for limiting condition we take is equal to, or we can keep on this inequality. So from here we can find the n value and apply the same inequality. So it's going to be mg cos alpha minus mv square by r should be greater than or equal to 0, that means mg cos alpha must be greater than or equal to mv square by r. This will say v square should be less than or equal to gr cos alpha. Now we can find the v value from v square from here. So v square from this equation is going to be v naught square plus this number. So v naught square plus that number should be less than or equal to gr cos alpha. Then we can simplify v naught square is less than or equal to gr. You can take common, bring all terms there. Then this is going to be this much. So v naught should be less than or equal to this. That means v naught should be less than or equal to this. That means maximum permissible value of v naught that we can accept is this number. So if velocity becomes more than this number, it will jump. If we want without jumping, so maximum permissible value is going to be square root of gr in bracket 7 cos alpha minus 4 divided by 3. It all numbers are within the square root. Now alpha is known to us, so we can find what is cos alpha. R is known to us, we can place here. G is 9.8 or 10, you can place. You can simplify this and you will get a numerical value. I am not calculating that value, you can calculate that. But yes, this is how we can get our answer. Okay. So that's the solution. Thank you.